Chapter 5, Ionics. Electrochemical was split into two stories. The first one is electrodics and the second one is ionics. Electrodics is about the charge transfer reaction or capacitive processes on electrodes. However, ionics is about the charge carrier movement through the body of media, which is the electrolyte. In this chapter, we will focus on the electrolyte or ionics. Let me start with the concept of electrochemical potential. Electrochemical potential is equal to chemical potential plus electric potential. So, mu sub I with superscript alpha indicates chemical potential of species I in alpha phase. In the same way, the electrochemical potential is the top bar with mu of species I in the alpha phase. Also, electric potential is the product of charge Z of species I with Faraday constant and the potential in the phase of alpha. What is chemical potential? Chemical potential is the first order partial derivative of Gibbs free energy with respect to the species I, the amount of species I. When temperature is fixed, pressure is fixed, and the other species is fixed. That is the chemical potential, which can be considered as the molar Gibbs free energy. Electrochemical potential is defined as the same way. Then in this case, our Gibbs free energy is about the chemical potential plus electric potential. Let me check some properties of the electrochemical potential for understanding the electrochemical potential. For an uncharged species or neutral species, the electrochemical potential is equal to chemical potential because G is going to 0. So there is no electric potential for the neutral molecules or species. For any substance, chemical potential is equal to standard chemical potential plus RT ln activity of the corresponding species. This equation is very same as the Gibbs free energy. When you derive the Nernst equations, we have started with this equation. Gibbs free energy is equal to standard Gibbs free energy plus RT ln activity. So almost the same because chemical potential is a kind of molar Gibbs free energy. So what is the meaning of standard state? Standard state means we have activity is equal to 1 for all involved species in this reaction or some process. So when A sub I super alpha is equal to 1, then the chemical potential is going to standard potential. The third property, for a pure phase at unit activity, it means, for example, solid zinc. You know, the solid material has its activity at 1, always. And silver chloride and silver, those three guys are solids, or hydrogen gases at unit fugacity, or in other words, unit activity. In that case, the activity term is going to 0 because activity is equal to 1. So for a pure phase at unit activity, the electrochemical activity is equal to standard the electrochemical potential is equal to standard chemical potential. One more thing. So for pure phase, all pure phase molecules or materials is neutral. So electric term also can be neglected. So electrochemical potential is equal to standard chemical potential for a pure phase at unit activity. For electrons in a matter, of course, the charge is -1. Then electrochemical potential is equal to the standard chemical potential plus for electron activity is going to 0, so you could neglect the activity term minus F phi potential, electric potential, because Z is equal to -1. Activity effect can be disregarded because the electron concentration never changes appreciably. So it means activity is equal to 1. The fifth rule is very important thing. For equilibrium of species I between phases alpha and beta, the electrochemical potential of species I in alpha is equal to electrochemical potential of species I in beta phase. Okay, so let me try to use the chemical or electrochemical potential concept for some chemical reaction, some precipitation, and finally electrochemical reactions. Here, all reaction in a single phase. Acetic acid is dissociated into proton plus anion, or vice versa. This is the weak acid dissociation equations. So let me build up balance equations. The total summation of electrochemical potential of the left side of this equation is equal to the total electrochemical potential of the right side of this equation. That is the balance equation. So acetic acid is equal to proton plus acetate. I forgot one more thing. So this balance equation is working only at equilibrium. I'd like to emphasize, at equilibrium, you have the electrochemical potential balance equation is working. This left side electrochemical potential is going to just chemical potential because the acetic acid has no charge. So you could neglect the electric potential. Then let's go to the right side of this equation. So the first term on the right side of this equation is going to the chemical equation plus chemical potential plus the electric potential. The charge of proton is +1, so +1 by F by phi. And also the second term is split into two terms like that. In the electric potential term for the second term has minus sign because acetate has minus. Then you could kill this term and this term. So finally, acetic acid, the chemical potential of acetic acid is equal to chemical potential of proton plus chemical potential of acetate anion. It means for a chemical reaction instead of electrochemical reaction, the electrochemical potential is just going to the chemical potential like that. All terms has only chemical potential without electric potential term. That is the first example for the application of the concept of electrochemical potential. Let's go to the second thing. Also, still we have chemical reactions instead of electrochemical reactions involving two phases without charge transfer. So without charge transfer means it is not the electrochemical reactions. Here, silver chloride, which is solid or crystal, is going to silver plus chloride minus dissociation reaction, or backward reaction is also available. On the right side of this equation, we have two kinds of ions, and all of them is soluble in solution. So solution phase and solid phase or crystal phase here. So let me set up the electrochemical potential balance equations. Silver chloride in solid phase or silver chloride phase is equal to silver plus in solution phase plus chloride minus in solution phase for the electrochemical potential. The left term is going to the just standard chemical potential, because silver chloride is solid, so that its activity is going to 1. So you could neglect the activity term for the chemical potential. And also there are no charge for silver chloride, so electric potential term is cancelled. So just standard chemical potential for silver chloride. And the first term of the right side of this equation is going to 3 terms: standard chemical and activity term and electric potential term. In that case, we have plus sign here. Also, the second term is going to 3, and for the electric potential term has minus sign. Then you could remove those 2 terms in terms of electric potential term. And then let me try to get together the standard chemical potential for silver chloride, silver plus, and silver minus onto the left side of the final equation. So those are 3 things. And then the left one on the left side of this equation is activity term, right? So RT, Rn, silver plus, activity of silver plus by activity of silver chloride minus. So this is a kind of equilibrium potential, especially for the precipitation reaction, which is the backward reaction of this reaction. This product of the ions, activity of ions, is called KSP, solubility, which is called solubility product, which is a kind of equilibrium constant. So that is the final equation for the precipitation reaction. And then let's go to the final example. Finally, we have met the electrochemical cell here. We have 2 copper electrodes. Copper itself is not very important thing. This is the electric conductor, and this is the cathode, and this is the anode. To distinguish the left copper from the right copper, then I have put prime for the left copper. So copper prime is for cathode, and just copper for anode. On the copper prime, we have silver chloride solid film. You should recognize silver chloride is solid and solid film. Then silver chloride is going to the silver plus Cl minus. Let me write down here. It is going to silver metal plus chloride minus. It means copper plus, actually this copper prime is connected to some potential state, and I have applied some negative potential onto the copper prime. So electron is going to the silver chloride. Then silver plus is reduced. Finally, silver metal is obtained and chloride minus is there. Let's go to the right side of this cell, and the second copper is connected to potential state, and the potential state provide get the electrons from the copper. So from the copper, electrons is going to the potential state. So zinc would lose electron to the copper. Then at the same time, zinc is going to zinc 2 plus. Then, okay, based on this knowledge, let me set up the chemical reaction equations, actually electrochemical equations. Zinc plus 2 AgCl plus 2 electron from copper prime is going to zinc 2 plus 2 silver plus 2 chloride minus plus 2 electron to the copper. That is the full cell equations. Of course, those 2 electrons could be removed to each other, but let me leave there on the left side and right side to set up the electrochemical potential balance equations. Then here we go. Zinc, silver chloride, and electron from copper prime is going to zinc 2 plus, silver in silver phase, and chloride minus in solution, and electron to the copper. Okay, then let me try to get together the electron term. This one and where it is? This one. Then we have this one. What is that? So the electrochemical potential is going to just electric potential, because standard chemical potential of electron is 0, and also the activity of electron is unity or 1, so that the activity term is going to 0. So only left thing is electric potential. So this one is going to electric potential, and the potential of copper prime minus potential of copper is going to cell potential. So minus 2 Fe cell potential. This one is going to there, and then let's go to the right side of this equation. So here, this one is split into 3 terms. And how about silver solid? Silver solid is going to just standard chemical potential, because no charge and activity is 1. So the other 2 terms are going to 0. How about chloride minus in solution? Split into 3 terms. And zinc metal, so only standard reduction potential like silver. How about the last one, silver chloride solid? The same thing, standard chemical potential. Then let me get together all standard chemical potential. This one, this one, this one, this one, this one. Here. What is that? That is the Gibbs free energy change at standard state. Right? And also, this standard Gibbs free energy change is going to the electric potential term, like my standard electric potential term, minus 2 Fe0. Then this is going to here, and the other term is the product of activity in log function with RT. So finally we have obtained this one. Electric potential or cell potential is equal to standard cell potential minus RT NF Ln, the product of zinc 2 plus and chloride minus. The other term is just 1. Everything is 1 except of those 2 ions. What is that? This is the Nernst equation. So, by using the concept of electrochemical potential, we have derived the Nernst equation. Okay, let me think about the ionic transport in electrolyte. So here is the overall pathway of electrochemical processes. The reaction is oxidized species gets some electrons, then toward reduced species. So here is the electrode and electrolyte. Some oxidized species existing in bulk solution is moved into the electrode surface. This step is mass transfer based on diffusion, convection, and migration. And on the surface of the on the surface of electrode, the oxidized species is adsorbed onto the electrode, and then get the electrons from the electrode, finally going to the reduced species in the adsorbed state. Desorption, and then the reduced species is going away from the surface to the bulk solution. That is the overall pathway, and the electrodics is about the charge transfer or capacitive processes around the electrode surface. However, for the ionics, we will study about the charge carrier movement in the bulk solution into the surface region of electrode. Then, let's think about the mass transfer. Mass transport have 3 different processes. The first one is diffusion, second migration, and the third one is convection. So mole flux is determined by diffusion, the driving force of which is the concentration gradient, and the migration, the driving force of which is the potential gradient, and the convection caused by some velocity. As you know, for the electroanalysis, usually we are trying to kill the second term and third term. So usually diffusion is used for the main driving force for making the current. In this equation, you could find some parameters or characteristics of electrolyte. The first one is diffusion coefficient or diffusivity. That is the first property of electrolyte, having ions or some species in the liquid medium. And the other thing is the mobility. Those 2 terms are the characteristics of electrolyte in ionics. So let me think about the mobility, diffusivity, or something like that. The first one is mobility. I have said mobility is the characteristics of migration, but this mobility is closely related to the diffusivity also. What is the mobility? Symbolized by U, which is a measure of how fast an ion moves under the influence of the electric field, symbolized by E. That is to say, mobility is the proportionality constant between the velocity of an ion or a charge carrier and the electric field strength. Here is the equation. Velocity of an ion is proportional to the electric field with its proportionality constant, that is the mobility. That is to say, the mobility can be considered as the velocity normalized by a unit electric field. Here is the situation. We have a red ocean, which is the media, like water or some organic solvent. And here we have an charged particle or an ion. This ion is moving at a constant velocity in the steady state situation. It means there are no net force exerted on this charged particle. It means we have two counter directional forces, and the intensity of the forces should be the same, but the direction is opposite. The left one is electric field force, and the other one is viscous force. Force due to the electric field, or F with subscript E, is charge by electric field. G is the number of charge and E is the charge amount, Coulomb. So GE is the charge amount, total charge amount with electric field. That is the electric field force. This movement due to the electric field is counterbalanced by a viscous force, which is described by the famous Stokes equation. FV, F viscosity, is equal to 6 pi eta. Eta is the viscosity of the media. And R is the size or radius of this green sphere. And velocity. So Fe should be equal to Fv to drive this charged particle at constant velocity. Then by reshuffling this force balance equation, then we could describe the velocity by the other terms. And here is the result equation. Velocity is something like that with electric field. It means this group of the parameters is going to the mobility. So again, mobility is equal to or proportional to the charge, and also the inversely proportional to the size of the charged particle. I'd like to emphasize that the charge amount and the size is the characteristics of the ion or this charged particle. Also, the mobility is determined by the characteristics of media at the viscosity of solvent. So again, the mobility is Ge per 6 pi eta r. If you have large charges, you have higher mobility. If you have larger particles, charged particles, it means you have a lower mobility. Also, if you have a very viscous media where you have the charged particle, then its mobility is going down. That is the mobility. And mobility is the characteristics of a single charge carrier. The unit is centimeter square per second per velocity. Per voltage. That is the mobility. And the mobility is the most basic characteristics of electrolyte. This is the starting point. The second one I'd like to introduce is conductivity, which is the another characteristics of electrolyte. Actually, that is the extension of mobility. Conductivity, kappa. Here is the current density, J of species I, the unit of which is ampere per centimeter square, is proportional to the velocity of the species I, of course, with some charge concentration term, Gi with F with concentration of species I. That is the charge concentration. Again, the current density is the product of charge concentration or charge density with the velocity of each charges. So let me check the unit. We should have ampere per centimeter square for both sides of equation. Ampere per centimeter square means Coulomb per second per centimeter square, right? And let's go to the right side. This is the moles of charge, so the unit is mole electron per mole of species I. The next one is Faraday constant, Coulomb per mole electron, and concentration of species I, so mole of species I per cubic centimeter, and the velocity centimeter per second. So the first three terms is going to Coulomb per cubic centimeter. It means GFC is the charge concentration or charge density with centimeter per second, and the product of those two units is going to Coulomb per second per centimeter square. So it is right. Again, current density is the product of charge concentration with velocity. And this velocity can be described by electric field with mobility. Then the first four terms is defined by conductivity of species I, kappa I. The unit of kappa I is Gman per centimeter, or ohm to the minus 1 per centimeter. So conductivity consists of two terms. The first one is charge concentration, and the second term is the mobility of each charge. Overall conductivity of electrolyte kappa is summation of kappa of each species. Molar conductivity of an ionic species I, lambda I, is equal to kappa I normalized by concentration of the corresponding species. So lambda I is proportional to Gi and Ui, mobility. Overall molar conductivity of electrolyte is lambda, capital lambda, which is obtained by summing all the molar conductivity of species I for all species. Where sometimes the overall molar conductivity, lambda, can be described by lambda plus lambda minus for one single salt, like sodium chloride. It means we have only one cation and one anion. In that case, total molar conductivity is equal to lambda of cation plus lambda of anion. So that is the conductivity. Again, I'd like to emphasize that the conductivity is the product of charge concentration and the mobility of each charge. Okay, so here again, the current density can be described by the product of kappa I mean the conductivity with electric field. Let me check the unit. Current density, ampere per centimeter square, and conductivity with volt per centimeter. So conductivity the unit of conductivity is ampere per centimeter square per volt per centimeter. So it means the unit of conductivity is 1 over ohm centimeter, or sometimes 1 over ohm is defined as Gman, S. So S per centimeter, Gman per centimeter. One more things. Actually, this equation is the Ohm's law. V is equal to IR. V is related to E and I is related to J. So the inverse of kappa is resistance. In the Ohm's law, we assume that the conductivity or resistivity is not the function of electric field. Independent of electric field, you should have the same conductivity and resistivity. However, in the real situation, we experience some deviation from this ideality. Y-axis is the kappa in this graph. Kappa means conductivity, and x-axis is the electric field. At low electric field or a small electric field, it is true that the conductivity is independent of electric field, actually constant in terms of electric field. However, at very high electric field, the conductivity increases. Why? This deviation of conductivity in terms of electric field has been explained by Wien effect. Here is two situations. The first one is about strong electrolyte. What is the strong electrolyte? It means your salt, like sodium chloride, is totally dissociated in electrolyte. So NaCl is dissociated into sodium plus and chloride minus. Each ions, especially cations, is solvated by solvent molecules or hydrated by water molecules. So here in your electrolyte, in your strong electrolyte, cations are separated from anions, and also the cations are totally solvated like that. At weak electric field, the solvated cations are moving with keeping its integrity. So the size of charge carrier, which is the hydrated cation, is larger than just pure cation. However, when you apply a strong or high electric field into the system, the cations originally surrounded by solvent molecules are going away from its hydration shell. So the charge carrier is just cation, not solvated cation. So the size of these charge carriers are smaller than before, so its conductivity increases with electric field. That is called the first Wien effect. The ions begin to move without solvent sheaths for strong electrolytes when you applied a high electric field. Let's go to weak electrolyte like acetic acid. There are still attractive force between cation and anion. So even in electrolyte, you have ion pair like that, minus plus. And in weak electric field, this pair is moving without losing its integrity. So the size of charge carriers are large than each cation or anion. However, when you apply very high electric field, cations and anions are divorced to each other, then each ion is working as a respective charge carrier. So the size of charge carriers are smaller than before. At the very first time, minus plus together. However, right now plus or minus. So each conductivity increases with electric field. That is called second Wien effect. So, for weak electrolytes, the dissociation of molecules increases due to the interaction of the electric field with their dipoles when you apply the high electric field into this electrolyte. Okay, so you have learned about mobility, also conductivity, or some variation of conductivity is going to molar conductivity. So here is the real value about the molar conductivity and also mobility. Let me check the values. So left compartment, you could find cations, and here upper side you have only one plus cation, and the bottom side has 2 plus cation. On the right side of this table, you have anions with 1 minus and also 2 minus. Let me check the equation of mobility and the molar conductivity. Mobility is proportional to the amount of charge. However, molar conductivity is the square is proportional to the square of the amount of charge. So it means the effect of the charge on lambda I molar conductivity is larger than the effect of charge amount on mobility. So, except of proton and hydroxide, the mobility is similar to each other for all plus cation and 2 plus cation. How about anion? Similar to each other, more similar to each other. However, in terms of molar conductivity, the 2 plus cations or 2 minus anions is always higher than those of 1 plus cation and 1 minus cation respectively, because the effect of charge is more important for the molar conductivity. I'll explain about the extraordinary value of the lambda or mobility for H plus and OH minus in the following slide. Before going to there, I'd like to focus on some alkali metal ions. Lithium plus, sodium plus, Rb plus, Cs plus. Actually, the size of these ions is increasing from lithium plus to Cs plus. However, no, it's a plus. And at that time, you could recognize that the mobility is continuously increasing. But our equation is saying not like that. I mean, if you have a larger size of your charged particle, then you do have smaller value of mobility. However, as the size increases, the mobility increases. the size increases, the mobility increases. Why? Let me check about the pure ion size and also solvated ion size. From this table, you could recognize that the size of pure ions is bigger as you goes from lithium plus, sodium plus, K plus, and Rb plus. However, surprisingly, the size of solvated ions show the size of solvated ions decreases from lithium plus, sodium plus, K plus, Rb plus. Why? Because of their number of solvation, number of the water molecules for solvation. The number decreases as you go from lithium plus to Rb plus. Let me check it. Lithium plus, about 5 water molecules each solvation sheath. Sodium plus 3.5 decreasing, and then K plus more decreasing 2.6, and Rb plus more decreasing 2.4. So the smaller number of water molecules for solvation is going to the smaller size of solvated ions, even if each ion size is larger than the other. So this Ri, the radius of species I, is the size of solvated ion instead of just pure ion. Then you could understand why the Rb plus mobility is larger than the mobility of lithium plus. One more thing. The K plus has its mobility at 7.6, and chloride minus shows 7.9 as its mobility. So the values are similar to each other for K plus and Cl minus. So KCl salt is well balanced in terms of mobility. I will explain about the KCl later. It's time to say about the extraordinary value of proton and OH minus. Okay, the mobility of the H plus is 36.2, which is much higher than the mobility of the others. The same for OH minus. Why? This is explained by Grotthuss mechanism. Again, proton aqueous and OH minus aqueous have much larger mobility than other ions, as they migrate via different transport mechanisms. That is the Grotthuss mechanism. The mechanism involves the rearrangement of bonds through a long chain of water molecules like that. Here is the H2O and neighboring H2O. At the very first time, the proton is attached to the first H2O. And then this proton is also has some interaction with the second molecules of water. Then the second bond between oxygen and hydrogen is stronger, as the first HO bond is weaker. Then proton is moving from the first molecule to the second molecule. Let me read this sentence. There is probably rupture of an OH bond in H3O plus here, and the rapid formation of a new OH bond here in a neighboring water molecule. So that is the Grotthuss mechanism, and proton and hydroxyl ions are extraordinary when compared with the other ions in terms of mobility or molar conductivity. Here is another property of electrolyte, that is the transference number. Transference number T of species I is the conductivity of species I per overall conductivity. The conductivity can be described by the mobility with charge concentration. Then denominator is the summation of those things. The summation of all the summation of transference number for all species is going to 1.0. It means 100%. Then also the summation is T plus. It means the total transference number of cations plus total transference number of anions is going to 1.0. For a single Zg electrolyte, G2Z electrolyte, G2Z means the number of charge of cation is equal to the number of charge of anion in a single salt. So for example, sodium chloride, this is the single salt, and sodium plus and chloride minus, G2Z. In that case, this equation is more simplified into the ratio of U plus per the U plus plus U minus, or this equation can be described by molar concentration also. Here is the table about the cation transference number. For example, HCl. As you know, the mobility of proton is much higher than the chloride minus. So its value, the transference number of HCl, would be larger than 0.5. So the really measured value is about 0.2 or more. Then let me focus on KCl. In the previous slide about the mobility, I have emphasized this sort because the mobility of K plus is similar to the mobility of chloride minus. Therefore, its transference number is around 0.5, which means the contribution of cation into the overall conductivity is the same as the contribution of anion to the overall the conductivity. So 0.5. The other thing is diffusion coefficient or diffusivity. Molecules and or ions move along a gradient of the chemical potential. So the driving force for the diffusion is, which is F, is the gradient of chemical potential of species I at fixed pressure and temperature. Then the chemical potential can be described by the standard chemical potential plus RT Ln, sometimes activity, sometimes concentration. So put it there, and then RT per concentration with gradient of concentration. That is the driving force for the diffusion process. And here, let me try to relate the diffusivity with mobility. So this is the mole flux. Mole flux is equal to current density per the charge amount. Then current can be described by the charge concentration with mobility with some electric field. Then by reshuffling this equation, then we could get together this one, I mean the charge amount with the electric field. That is the driving force. So this is going to F. And then let me use this equation. Put there. So we have this one. And you could cancel concentration term and concentration term. Then a group of some constant and the properties of electrolyte with concentration gradient. So I could say diffusivity is mobility with RT per charge amount. This one. Could you say diffusivity is depending on the charge amount? No, I don't think so. Because mobility has a term for the amount of charge. So after putting the mobility equation into the diffusion equation, diffusivity definition, then diffusivity of species I is equal to RT, some constant, per 6 pi viscosity of your solvent with the size of your particle or charged particle or ions. It means diffusivity depends on the solvent property eta with the size of ions. However, the charges of ions are not related to the diffusivity. This is the last subchapter 2, liquid junction potential. What is the liquid junction potential? Shortly, LJP. Here we have a electrochemical cell, copper and copper prime, which are the electrodes, and on the right side of copper prime you have copper 2 plus in electrolyte. So there is some reaction between copper and copper 2 plus. Also, let's go to the left side. On the copper electrode we have zinc metal, and zinc metal is dissolved into electrolyte as zinc 2 plus ions, or sometimes zinc 2 plus is electrodeposited as a form of zinc metal on copper electrode. So that is the electrochemical cell. Let me say the zinc 2 plus containing electrolyte is alpha phase, and copper 2 plus containing liquid while electrolyte is beta phase. Between alpha phase and beta phase we have a semi-permeable membrane. So we could divide the electrolyte into two parts. Again, alpha phase and beta phase. And then let me check the cell potential. So the potential of copper prime minus beta phase plus beta phase minus alpha phase in terms of potential plus alpha phase minus electrode, in this case copper or zinc, which is connected to each other as a electric conductor. So the same thing, copper and zinc. So in this case I'd like to say alpha here minus just copper, sometimes zinc, anything is okay. So we have three terms for the overall potential of electrochemical cell. Then let me reshuffling it. This one is going to here and this one is here, but minus sign, then change the order of alpha and copper to copper and alpha plus beta minus alpha. What does it mean? The first potential difference term is about the potential difference between kappa prime and beta, which is the potential difference around the interface between electrode and electrolyte. And also the other thing is the potential difference around the other interface between kappa electrode and alpha phase of electrolyte. Usually we are thinking about the potential difference, which is the sum of those two interfacial potential difference. However, we cannot neglect the third term, the potential difference between beta minus alpha. This is called liquid junction potential. If you have just one phase electrolyte, then there is no liquid junction potential. However, sometimes you would have two different electrolyte, which is divided by semi-permeable membrane. In that case, you should think about the potential difference between the two phases of electrolyte. That is the liquid junction potential, shortly LJP. Three types of liquid junction potentials are here. The first one, type 1, is the concentration liquid junction potential. Here is the situation. We have two compartments for the electrolyte. Between them, we have a semi-permeable membrane. In this case, we have the same electrolyte, HCl. But the difference is the concentration. On the left side of the semi-permeable membrane, we have 0.01 molarity of HCl. However, on the right side, we have more concentrated 0.1 molarity of HCl solution. In this case, we have a higher concentration of HCl on the right side, so proton and chloride minus is moving from the right side to the left side. At this point, I'd like to compare the mobility of proton and chloride minus. I have said the mobility of proton is much higher than the other cations and anions. So proton is moving faster from the right to the left side, but chloride minus is moving slowly. So the left part is charged by negative ions. Positive ions, because more amount of proton is moving to the left when compared with the chloride minus movement. So you would obtain the positively charged electrolyte on the left side. However, at the same time, you would have some negative charges on the right side. So we have the difference in charges between those two phases. It means some potential is developed. That is the concentration liquid junction potential. Let's go to the type 2. In type 2, we are using the same concentration of electrolyte. However, on the left side we have HCl, but on the right side we have KCl. That is to say, the different thing is cations. Proton is moving from the left side to the right side because on the left side we have a higher concentration of proton. However, from the viewpoint of K+, the movement direction is going from the right side to the left side. However, the mobility of proton is higher than the mobility of potassium plus. So, the right side compartment is positively charged, while the left side of compartment is negatively charged. It means we have some potential developed between those two phases. Let's go to the last and most complicated type, type 3, liquid junction potential. Concentration, different, and the cation and anion is different. So proton moving to the right side, also chloride minus going to the right side. However, proton and nitrate ions is moving to the left side. However, the mobility of proton is much higher than the mobility of chloride minus, K plus, and nitrate anion. So the right side positive, left side negative. So some potential is developed between them. Let me focus on the type 1. Here, beta phase and alpha phase. Cation same, anion same. However, we have a higher concentration in alpha phase. Alpha phase, we have 1, 2, 3, 4, 5, 6. 6 plus and 6 minus are there. On the other hand, in beta phase, you have 2 minus and 2 plus. So, plus ions and negative ions is going from the right side and right side to the left side due to concentration gradient. Let me assume that the mobility of anion is higher than the mobility of cation. For example, KOH, OH minus is moving fast. However, K plus is moving slowly. So, more amount of minus ions is moving to the left side. However, smaller amount of positive ions is moving to the left side. Finally, we have this kind of situation. Only 1 plus is moving from the right to the left. However, 3 more minus ions are observed on the beta phase. So, net charge of beta phase is 2 minus, net charge of alpha phase is 2 plus. So, potential is developed. Net charge develops due to difference in mobilities. Then, Q is the net charge. In this case, 2 charges, 2 plus, 2 minus. And then, potential is developed by this net charge, which is divided by capacitance. So, we should think about the potential difference between electrolyte in this case. Okay, so right now you have a concept of liquid junction potential. And in this example, let me try to develop some equation about the liquid junction potential, and also let me try to calculate some values. Here is the cell, and we have 2 platinum electrodes. And as an electrolyte, we have hydrochloric acid for both phase. 2 liquid phase regions are there, and between them we have a semi-permeable membrane. So on the right side of the semi-permeable membrane, we have beta phase of electrolyte, maybe some concentration of HCl there, and on the left side of this permeable membrane, another concentration of HCl is there. So this schematic picture of an electrochemical cell can be described by this notation. So platinum and platinum prime. And in the alpha phase of electrolyte, you have hydrogen gas 1 atm with proton in activity 1 with chloride minus ion. Also on the beta phase, you have the same thing, but activity is different. On anode side, hydrogen gas is oxidized into proton in alpha phase, and on the cathode, the proton on beta phase is reduced into hydrogen gas. So hydrogen is going in and going out. Net electrochemical reaction is proton in beta phase plus electron from platinum prime is going to proton in alpha phase plus electron to platinum. Then here is the electrochemical potential balance equations. So proton in beta, electron in platinum prime is equal to the proton in alpha plus electron in platinum. Then let me get together the electron term here. Then this electrochemical, this difference of electrochemical potential of electron between PT prime and PT is the cell potential with Faraday constant. Is equal to the electrochemical potential difference of proton between beta phase minus alpha phase. Then each proton electrochemical potential is split into 3 terms, and from both terms, both electrochemical potential of proton, we have the same values of standard chemical potential. So you don't need to think about the standard chemical potential because here is the minus. And the other 2 terms is here, activity term and the electric potential term. So E is cell potential is equal to RT NF ln activity ratio. What is that? That is the Nernst equation. But the cell potential is not expected from only Nernst equation because we have liquid junction potential. So simply I could say the cell potential is Nernst potential plus liquid junction potential. Of course, if you don't have any semi-permeable membrane and any difference between any difference of the concentration between those 2 phases, of course the liquid junction potential is going to 0. So cell potential can be expected by Nernst equation. However, in this situation, 2 different concentration, then you should think about the liquid junction potential. And also, this liquid junction potential is a kind of loss in terms of the potential. I'll show you the loss of potential by liquid junction potential in the detailed example in the following the slide. Anyway, let me try to calculate the liquid junction potential. Here is the charge transport at the junction, and based on this charge transport, we could develop some balance equations. Here is the electrochemical potential difference between alpha phase and beta phase in terms of chloride minus. And this is the electrochemical potential difference of proton between beta and alpha. Those 2 difference of different species is correlated with transference number. So on the left side of this balance equation, the product of transference number with the potential, actually electrochemical potential difference of chloride minus, is equal to the product of cationic transference number with the difference of electrochemical potential of proton. Then this electrochemical potential of ions, sometimes chloride minus, sometimes proton, then it is going to activity term plus electric potential term for the H plus and for the chloride minus. For the chloride minus and for the H plus proton. But still, electric potential beta minus alpha is the same thing. Not especially for this one is chloride minus, this one is proton minus. This is the common thing. So let me try to get this beta minus alpha in electric potential. This is the junction potential. It's equal to minus the transference number difference RTF Ln activity terms. So actually this one is the Nernst equation. And for calculating the junction potential, you should add the transference number difference in front of the Nernst equation with minus sign. So this is the loss of potential. Okay, so we have developed the junction potential equations. So here is more general equation about the liquid junction potential. Liquid junction potential is minus, I have said about the minus RTF. This one is the Nernst equation, but you should have this one, the transference number term per the amount of charge. For cation, this is the plus signs, and for the anion, this is the minus sign. So if you have plus 1, minus 1, then this term is going to the transference number difference. Okay, then here is some several equations. More rigorously, the junction potential can be described by Henderson equation, just for your reference. This equation is enough for this class. Okay, those two equations is for the type 1 liquid junction potential. How about the other type? Here is the type 2 junction potential. In that case, you have used the lambda, beta, lambda, alpha. That is the conductivity of beta phase, and this is the conductivity of alpha phase. Plus sign is for common cation in type 2, and minus sign is for common anion for type 2. To minimize liquid junction potential, this one, I have said liquid junction potential should be considered as the loss of potential. So we should minimize this junction potential. To minimize liquid junction potentials, we are using a salt bridge. And in the salt bridge, usually we are using KCl because there is no difference of mobility between K plus and Cl minus. Therefore, the liquid junction potential could be minimized. Here is the effect of a salt bridge on measured junction potential. I have varied the concentration of KCl involved in the salt bridge. So we are going from 0.1 molarity of KCl to higher concentrated 4.2 more KCl. Then in that case, junction potential decreases from 27 millivolt to less than 1 millivolt. So by using salt bridge having higher concentration of KCl, you could depress the liquid junction potential. Okay, here is some numbers. Let me calculate the real values of liquid junction potential. We have the same electrochemical cell, and the beta phase has 0.1 molarity of proton, and in the beta no, this is the beta phase, it's 0.1 molarity of proton, and this is the alpha phase, and the proton concentration is 0.01. I mean, higher concentration is available on the right side of electrolyte, and the less concentration of proton is found on the left side of the semi-permeable membrane. So Let me try to calculate the cell potential. RT per F at room temperature is going to 26 millivolt, and ln A2 beta phase 0.1 per 0.01. This value is plus 60 millivolt. I mean, in this cell, plus 60 millivolt is developed between two electrodes. However, we should consider the liquid junction potential. Let me calculate the liquid junction potential here. So, this is the Nernst equation, 60 millivolt, and here is the difference of transference number between proton and chloride minus. Proton 0.83. The chloride minus 0.7. The difference is about 0.6, right? 0.2, 0.0, less than 0.6. And then you should put the minus sign here. Then liquid junction potential is minus 40 millivolt. So originally, without liquid junction potential, the potential of platinum on the right side of this cell is 60 millivolt higher than the platinum of the left side of this cell. However, with liquid junction potential, this cell potential is decreasing from 60 millivolt to 20 millivolt because some potential is consumed by the interface between beta phase and alpha phase, or consumed by liquid junction. So total cell potential is plus 20 millivolt rather than plus 60 millivolt. In this case, the liquid junction potential is serious, so you will lose some potential by the liquid junction. That's it for the ionics in chapter 5, and we have one more example, and this is for your job.